Yeah. It feels like it's been a while. Yeah? What happened? Spring break happened, exam happened, huh? Yeah. Ah, that's right. That's why I feel like I haven't been in this classroom for a while. Okay, okay. Good. Well, how was the exam? Smiling at me. Somebody said, huh? Better smile. No comments? What did you say, Kevin, to me last time? It was tricky, he said. You agree? It was tricky?
We should have more time to think. Like 1 hour for me was little.
Not enough time to think? Hmm. You overthink. I think I haven't had a chance to look at them yet. Actually, I just got them yesterday. They forgot to give it to me when I came back. It was still in Echo's office and I forgot to ask them. So anyway, but I just got them yesterday. I will start looking at them this weekend. It's been a busy week for me anyway. Um, and then I think I was talking to Kevin about that. Um, for some reason, in 2021, somebody asked me if we can have a take-home exam for the second. And I said, okay. And in 2023, I offered the same, and they said, okay, they wanted that. Do you want to take home exam for the second exam, or do you want to take it in class? You want more than 1 hour to do. Yeah, it's not going to be any different. It's just really my exams are whether you have open books or not, it's the same thing. You got to study and think about it and link things together. So I don't mind having it a take home exam. So do you all prefer a take home exam? Designate by raising your hand. Miriam, do you want to take home exam?
Yeah.
Yeah, okay, good. So since everybody says yes, it will be a take-home exam. I have actually an example of a take-home exam from last offering. So you'll see it's pretty much similar style, but then you have more than an hour to think. Yeah. But again, I don't want you to stress over it, you overthink it, but we'll see. I will open the what's that? Take home exam?
Yeah.
You'll have actually, you can print it and write on it.
It's online.
Not online, not online. It's a take home. You can just print it, write, and give it to me. Yeah. I think so. I don't remember how I did it last time. I have to check, but I think it's just maybe I even print it and give it to you printed. So yeah. Okay. Um, was there anything else I want to say? Yeah, presentations. So we start next week with our first two presenters. So we have VT and Medora. And just a reminder, please make sure that you give yourself time to meet with me at least half an hour, few days before your presentation. What I want to do is make sure, well, make sure have your slides ready. I'll go over the slides with you, make sure you have the correct format and what you need to cover, plus making sure that you link concepts we learned in class to your presentation. And anything new would be good to highlight as well, if we didn't cover it in class. Huh? Yes. Not for sure. If you not for sure. That's it's part of like you don't have to cover everything in the paper. So the most important results are results that will basically connect to what we covered in class. So some papers have like what, 10 figures and tables, and we don't need to see everything they have in that. So it is kind of an artic presentation, and you all have to be concise and give the message. So, yeah, so those things are 10 minutes. Okay. You can do it. It can be done, right? You, some of you did the orientation class. You did it in 10 minutes too, right? Yeah, it can be done. And I'll help you. That's why make sure you have a half an hour with me a few days prior. So I'll guide you through it. And don't forget in the syllabus, there is on page 3 of the syllabus, there is the presentation description. So make sure you read that and also look at the evaluation forms. It will also guide you to what things you will be graded on. So it will help you as you prepare. Both, of course, are on Canvas, this information. All right. So we're going to dive into a new topic. It's enzymes. Enzymes are important in so many aspects in food, whether they are used as processing aids or used for many different things. We will talk about that. So they're important, and they are maybe proteins. This is the question now. All right, are they or are they not? What are they? Do we need, is the lighting off a little bit? Better. So, what did you say? A? What do you say? How do you, huh? Only C?
No.
Oh, only.
Not see.
No, not see.
Well, C, enzymes decrease activation energy. Enzymes are made up of amino acid only. Enzymes are protein. Come on. All right, we'll answer that later. I have story. Okay, so this is to show that enzymes can may have multiple components. So sometimes you have a cofactor, we call it a coenzyme. This can be an organic molecule, metal, or any molecule that will bind to the enzyme and then will enhance the activity of the enzyme. So there are different nomenclatures that you will see. Apoenzyme is the enzyme with like the protein portion, but it's not active. Once you add a coenzyme, then it becomes a haloenzyme, and then it becomes active. All right. You remember KM? You know, you learned it in so many different places, but I don't know why, it's always forgotten. What is KM? Who is the brave soul that is gonna try to define it? Okay, go ahead, Shri. What's that?
The rate of the reaction.
Unholy. Any more thinkers? Do you change your mind?
Concentrate on products rather than concentrate on reactions.
Good, then get creative. No more thinkers? Come on. Tuki, help us out. Well, first of all, it stands for Michaelis-Menten constant. These guys, Michaelis-Menten, they came up with the Michaelis-Menten equation that we are going to spend time deriving. And what is it? The constant. It's the concentration of the substrate where V max is at half V max. It's at half the maximum rate of the reaction. It's not the rate of the reaction. It is the substrate concentration at which the velocity equals half V max. Okay, we're going to talk about it quite a bit because it's important in determining which enzyme to use with what substrate and whether we want to inhibit the enzyme or we want the enzyme reaction to proceed. Depending on the purpose, Km plays a really important role. So, knowing that this is Km, what is it? When the substrate concentration is much greater than Km, what happens? Do you remember this? Oh, I think I discovered that I can write on the slides. Hold on. How do I do this? I need to. And then. Yeah. Let's see if I can read it. I don't know why it does that. Okay, forget it. I wanted to do that for the sake of people online, but all right. So you remember the curve that looks like that? What's here? And what's here? Time. Well, yeah, time. I'm going to do this. So you have an enzyme and you have a substrate and the reaction is progressing. So what is here? Substrate product, what is it? Product. Here. What is the slope equal to? When you have time product, the slope is equal to initial velocity. So now you have velocity at a specific substrate concentration. If you have here substrate concentration, and then here you have initial velocity, then what we have this is here is V max. Km. Is here. And this is V max over 2. So now if you see this, can you answer the question? A first order reaction with respect to substrate is obeyed, which means as the substrate concentration increases, the rate of the reaction increases. That's what first order means. Zero order, the reaction rate is independent of the substrate. Or zero order with respect to the enzyme, or the reaction rate is independent of the enzyme. So when the substrate concentration is way out here, so is it first order or zero order with respect to the substrate? Zero order, right? No matter, it's up there, you reached V max. So no matter what if you change the substrate concentration, the velocity is not gonna change. So at substrate concentration much greater than Km, it is actually zero order with respect to the substrate. So A is wrong. And C is wrong. It is first order with respect to the enzyme. So when you're measuring enzyme activity, you really want the enzyme activity to impact the reaction rate, because you will need to calculate enzyme activity. So in order to calculate enzyme activity, you want to saturate the enzyme. So you want to make sure you have substrate at saturation level way above the Km. Then the velocity will be impacted by the concentration of the enzyme. Then it will be first order reaction with respect to the enzyme. So be it. Okay, we'll get more into it. This is just a little taste of it. Okay. So tell me why enzymes are important in food systems. Tell us how we use them, or what do we care for them? Why? Give examples.
This is also constant, the above in particular concentration, right? So that means that is going to be also zero total because of the enzyme.
No, this is when you plot this, you plot it at a particular E concentration. So at a constant enzyme concentration, you get your plot. Yeah. There will be another, so here's enzyme concentration and here's velocity. You have that here. To a certain extent until you deplete the substrate. Until substrate is depleted, then you have it. So here, enzyme and velocity. Then this is first order with respect to enzyme. Okay. Come on, examples, use of enzymes to make ingredients, such as, like what kind of ingredient? Huh? Okay, yes, high fructose corn syrup. Okay, so it is a processing aid. It's used to produce ingredients. Okay, very good. What else?
Breakdown,
Breakdown.
components that we don't learn, like example, lactose.
All right, very good. Yes, breakdown components that we don't want. What we do? Nothing?
Products and cheese.
Yes, part of processing, producing cheese. Yes, what else? Digestion.
Little tangent, but like.
Outside of the body digestion, food system.
Yeah,
And food system, and producing protein hydrolysates.
and then also like TV pass.
For measuring tool, yeah. Used for measuring, in experimental setting. Measuring total glucose, for example. So it's used in analysis. Huh?
And you also quality like the ground.
Quality, absolutely. So when we are looking for polyphenol oxidase activity, we're looking at enzymatic browning. Yeah, so there are a lot of applications. So you named quite a few. Quality polyphenol oxidase, or for example, sometimes you want to measure lipoxygenase activity for oxidation of lipids. Sometimes you want to measure alkaline phosphatase. Why do we want to measure alkaline phosphatase? We just talked about the test pasteurization. Processing tool, so reducing cheese. What else did you say, Nicholas? We could do? Yes, ingredients, like high fructose corn syrup. Waste management, sometimes when you have co-products that are rich in carbohydrates or lipids or protein, so you add enzymes to break them down so that you don't cause sewage problems and waste problems. Sometimes we need to quantify inhibitors like trypsin inhibitor, for example, or amylase inhibitor. We really need the enzyme to determine the inhibitor activity or presence. Quantification of food constituents, dietary fiber, for example. Some of you do that. So you need to digest things during the analysis to get the dietary fiber. Glucose, for example, if you're doing total starch, you break down the starch into glucose and then you by enzymes, and you also use another enzyme to determine glucose amount. So enzymes are really important. You encounter them every day almost in your daily routine, whether you're working in a lab or you're eating cheese or you're digesting food. So enzymes are important, but in food systems, they are important and we use them or we measure them, like measuring their activity, for example. Let's say you want to produce a set amount of curd, cheese curd per day. So you want to know what's the minimum amount of enzyme you need in order to produce a certain amount of curd in a certain amount period of time. So you don't want to overuse enzyme because enzyme money costs. So you want to understand the kinetics of the chymosin that you're using, different chymosins from this microbial chymosin or animal chymosin will have different kinetics. So you really need to understand the kinetics so that you know how much substrate to enzyme you need, what's the optimum temperature, what's the optimum pH. Do you have inhibitors in the system that you want it to be inactivated? So enzyme kinetics are really important to set your reaction parameter. That's from like production, but let's say you are trying to inhibit polyphenol oxidase in certain application, you don't want browning. So you also need to know what kind of inhibitor I want to use, competitive inhibitor, non-competitive inhibitor, uncompetitive inhibitor, two types of inhibitors. What inhibitors do I use? I need to understand the kinetics in order to choose the inhibitor. So these are just few examples of why we need, you're designing an experiment, glucose oxidase, how much, what's the pH, the temperature, how much of the substrate to enzyme I need to use, in which time that is. Do I want my reaction to be 5 minutes or do I want my reaction to be 30 minutes? In what situation I would choose what? To control the reaction and be able to control it. So a lot of factors we need to know, and we know these factors through understanding enzyme kinetics. Yes.
What is uncompetitive?
You're coming to it. We're going to talk about it. There are different forms of how the inhibitor binds with the substrate or with the enzyme to prevent the reaction from going forward. There is competitive, non-competitive, and uncompetitive. I'll show. I have drawings to show later. Okay. So what's the definition of enzyme? Let's go from the very beginning. How do you define an enzyme? Simple. What do they do? Huh? What is that something?
But it's activation energy.
No, not protein. She said it's protein. Ice. Huh?
Just the activation energy.
What do you call this little substance that enhances the reaction? Catalyst. It's a biological catalyst. Okay, so it's a biological catalyst then that decreases the activation energy and allows a conversion of a substrate into a product. And the enzyme is not consumed in the reaction, so the catalyst is not consumed in the reaction. It is released and goes back to act on the rest of the substrate. Until most of the substrate is depleted, the rate of the reaction slows down. Okay, now the story of are enzymes proteins? Yes, you agree? Well, way back about over 100 years, a century ago, people thought they were proteins. And then researchers started to isolate, purify, to characterize the activity of the enzyme. And then a German scientist, Willstatter, was him and his group, they were able to isolate peroxide. And they measured high activity in this isolated solution or enzyme solution, high activity. When they measured protein, they couldn't find protein. So they deduced enzymes are not proteins. Sumner is an American scientist from Cornell, specifically, isolated another enzyme, and they actually crystallized the enzyme and determined it's a protein. So of course, the Europeans sided with Willstatter. But Sumner won. He got the Nobel Prize for the discovery and ended the debate, or so we thought. But can you tell me why Willstatter did not find protein in his isolated enzyme? You got it, and I'm looking. Yeah.
Is it the method that was not compared to the type of enzyme? The method that you use?
Not sensitive enough to detect, because enzymes act at a very, very low concentration. They're catalysts. So they have high activity at low concentration. So the method that they use to detect protein, I don't know what the method was, is not sensitive enough to detect protein in his isolated solution. So that was why he concluded they're not protein. And then these guys came along and discovered and got the Nobel Prize for the discovery that there is non-protein enzymes in biological cells. What are they? Ribosomes. Ribosomes, or ribozymes, they are the rRNA, adenoma RNA. So they have catalytic activity in the cells that simulates the protein enzyme. So not all enzymes are proteins, basically. The answer is, but enzymes that we deal with in food systems are proteins. So that's end of the debate. So from now on, we're going to consider them proteins. It's good history lesson here a little bit. Okay. So over the years, identification of enzymes started by purifying these enzymes using chromatography, electrophoresis, other techniques based on solubility, and there's almost over around 3,000, now maybe it's over 3,000 enzymes that have been purified and characterized for their activity. So there are many, many enzymes out there. So enzymes have been sequenced through genetic sequencing, looking at structure by NMR, and they were determined, some of them to be homogeneous, made only of amino acids, some of them are heterogeneous, they have non-amino acid components, and they range in molecular weight from 12 kilodalton to about 1,000 kilodalton. Enzymes can also be synthesized if we know the gene, or the gene can be isolated, so enzymes can be synthesized. Now, moving on, how do we name those enzymes? Every enzyme has a commission number. This EC is a commission number. Every enzyme that is identified and is listed and has a commission number. We also have trivial or common names. We have systemic names. Trivial names, trypsin, peptine, pepsin, just their known common names. But then we have names based on substrates, like protease, lipase, lactase, huh? Okay.
Polymerase.
Polymerase.
I'm just naming aces.
No, not the eggs, the
Yeah.
substrate, so it's the substrate that they act on. Okay, so sucrase, lactase, that, yeah. And then they can be named based on the type of reaction they catalyze. We have 6 main types of reaction. So oxidoreduction reactions, so they're known as oxidoreductases. Hydrolysis, known as hydrolases. Transferases, those that can form or break double bonds, we call them lyases. Isomerases, for like converting glucose to fructose. When you produce a high fructose corn syrup, this is an isomerase, changing it from one isomer to the other. Ligation, which is an enzyme that catalyzes a covalent reaction. So in food system, mostly you would encounter oxidoreductases, hydrolases, transferases, and isomerases. A lot of the examples in food systems have those 4 types of reaction. And these are examples of putting things together, the substrate and the type of reaction. So hydrogen peroxide is a substrate. Oxidoreductase. Another name for it is catalase or peroxidase. And then glucokinase, so the substrate is D-glucose 6-phosphate, and then the reaction is transferase type of reaction. And so on. This one is a hydrolysate, triglycerol acyl hydrolase. So you are hydrolyzing a triacylglycerol by using lipase. So a little bit of how we name enzymes. So enzymes have specificity. Most of the time they are very specific to a type of a reaction. So they have to bind with the substrate. We call the binding stereospecific type of binding. So it has to do with the stereochemistry of the compound. So there is a binding site, and then there is the active site. So the active site of the enzyme and the binding site of the substrate, they bind stereospecifically. So the binding has to occur for the reaction to happen, and if they don't bind correctly, the reaction doesn't happen. So Yeah, oh, is the binding covalent or non-covalent? Non-covalent. It is a reversible reaction, so it's not a covalent. The binding of the substrate to the enzyme is reversible, but once the substrate goes to a product, it's not necessarily reversible if you don't do anything to bring it back. All right, so now over 100 years ago, so they came up with the theory of locking T theory. So you have to have, like you have a specific T for a specific lock. So the binding is stereospecific, which we know, but also it used to be thought that the active site is rigid, meaning it doesn't change. Either the enzyme fits it, or the substrate fits it, or not. Is this correct? No, it's not. It's still, you need to have a stereochemical or stereospecific binding, but it is not, the active site is not rigid. Actually, it kind of changes based on the environment. And also it kind of allow the substrate to bind and takes the form that allows an accurate binding or a stereochemical binding of the substrate to the enzyme. So that form on the enzyme, which is protein, you know that when the pH changes, you have different ionic. The active site is where the enzyme can bind this up. Yeah, the active site of the enzyme. For example, you want to lactase. That's what breaks down that specific bond is. Yeah, looking down. Yeah, but it has to bind, that substrate has to bind to the enzyme. Oh, before it breaks it. I got the specificity of that enzyme. Well, the active side dictates specificity. So lactate has a specific active site that will bind to lactose. It will not bind to lactose. There is no stereochemical interaction of lactate with lactose. So imagine two reactions is going to happen. So your enzyme and substrate will bind to give ES complex, enzyme substrate complex. The rate constant of this reaction is K1. So going from E enzyme and substrate, getting a complex, that is one reaction and the rate constant is K1. And then what happens is two reactions, the ES disappear. So it disappears, either it goes back because it's a reversible interaction. It's not a covalent. So the ES will go backwards or forward to produce a product and regenerate the enzyme that goes back and binds with the substrate. Of course, you can drive the reaction forward more if the enzyme is saturated with the substrate. If you have high concentration of the substrate, you are really driving the reaction forward. So now you have three reactions going. The appearance reaction, appearance of ES is K1 is the rate constant. The disappearance, you have the K-1 going backward and the production of the product going forward. So you have three reactions, three rate constants. Yes, you can if you have way to economically separate the enzyme or retain it. course, you lose stability and activity over time. Like anything, we age, we grow, we become non-active, we denature, you know. But if you do, for example, we have applications where you enable this enzyme on membranes. Then you run through your sample with a thin milk too, with the lactase immobilized. So if the milk goes through and the lactase breaks down lactose into glucose and galactose. It's a continuous process and the enzyme is revived. But at some point, your enzyme will be, nobody lives forever, not even enzymes. But they are reusable. Yeah, you do lose activity over time in general. Even if you have your enzyme sitting in the refrigerator or the freezer, you lose activity over time. Okay. Oh, of course it's not going to work. Hold on. So enzymes reduce the activation energy that is or the energy needed to convert a substrate into a product. So in the presence of enzyme, the reaction rate is sped or it is accelerated about 1,000 to the 10 or 10 to the 11th times, depending on the enzyme, depending on substrate, depending on the reaction. So basically, it makes the reactions occur more efficiently. So the rate of the reaction or the velocity of the reaction is obviously dependent on so many factors. Increase the enzyme, you have faster rate of the reaction, right? But it doesn't exist in vacuum. You can increase the concentration of the enzyme, but if the substrate is depleting, no matter how you increase the enzyme, you won't increase the reaction because now you are losing substrate. So we have other dependence or other factors like the concentration of the substrate. Do you have inhibitor in the system? And do you have the necessity cofactors? Some enzymes require, for example, magnesium to work, calcium, sodium to work, or other cofactors. Cofactor is a part of anything. I was going to get to that. There is a cofactor that binds very strongly, and once it's bound, that's it. It has very low dissociation factors. Some cofactors are reversible, so they bind, the reaction happens, and then they unbind. Yeah. So there is irreversible and reversible, and there are two different types of cofactors. All right. So not only substrate inhibitors, cofactor, enzyme concentration, the conditions, the environment. So you already know that you need an optimum pH, for example, for different enzymes to work, and you need optimum temperature. And you need specific ionic strength, because these conditions impact the shape of the active site, the ionization state of the substrate, for example, if they are ionizable, and the enzyme. So that's why every enzyme have a different pH that would have highest activity, temperature, and ionic strength. In general, it's just thought that the velocity will decrease by 0.5 times when we are 1 pH unit away from the optimum. And the velocity decrease up to 2 times when the temperature is 10 units below the optimum. Of course, with enzymes that are protein, once you get to a denaturation temperature, you increase the temperature, you get to denaturation, then the activity goes. So it's not like every 10 degrees you're going up. Okay. So because of all of these facts, yes, that's true.
Can you also use product concentration to increase the rate?
Okay, so the product sometimes it's not just the product that's independent of the substrate. To deplete the substrate, even if you deplete the substrate and you take away the product, you don't have enough substrate in that thing. But I think what you're saying is you have an inhibition effect of the product. If you have a lot of product, they might act as inhibitors and slow the reaction. But in general, substrate has a more impact on the rate than. Okay. So because of all of this, all of these factors, again, when we are designing an enzymatic reaction, whether to produce an ingredient or for food processing or to run a reaction for quantification, we really need to know what the conditions should be like. So, and in order to know this, we have to understand enzyme kinetics. That means we need to determine what. When I say enzyme kinetics, what am I looking for? I need to know. Okay. What did I start? The first question I asked you to do. Km. I need to know the Km. I need to know K max. I need to know the Km. I need to know the V max. And then I need to know at which conditions I'll get the best V max for the highest V max and the lowest Km. Well, I kind of said why it's important because we need to design enzymatic reactions for different purposes. In order to design these enzymatic reactions, we need to understand the kinetics and determine important factors. And this is my graph here, which will lead us to Michaelis-Menten equation that we use to determine Vmax and Km. Okay, so when you start an enzymatic reaction, if we don't know anything, then you just mix specific, you start with the concentration of an enzyme and concentration of a substrate. This graph or figure you plot at a constant concentration of enzyme and a constant concentration of substrate at a particular pH and temperature. So everything is constant. And you just monitor product production over time of the reaction. So everything else is constant. You're only looking, you mix things up, you incubate it at particular environmental conditions, and now you're measuring product over time. So if you take a measurement after certain intervals, you come up with something that looks like that. So the initial here, we call the initial phase, we call it pre-steady state. So what's happening here is when you incubate the enzyme and the substrate, because no concentration of each, and you put them together, there's a little bit of time, a very short period of time, where binding happens to form ES. You cannot get the product before you start forming your complex. So that initial stage is the pre-steady state where we are producing ES. When ES is formed, then we get to a steady state where then we get the reverse reaction and the forward reaction, where we get at the steady state, the rate of disappearance of the complex ES equal rate of appearance of ES. So the disappearance, meaning going forward and backwards, and the appearance, meaning going E plus S, giving you the ES. So you have the forward, which is the appearance to get the complex, and then you have a disappearance, which goes two ways, forward to give you the product, and backward associated back into E plus S. The steady state, you can see, is linear here. So that steady state linear, where the product relationship to time is linear, so there is, with increase of time, there is steady increase in product. The slope of that is your initial rate of the reaction, V0, initial rate of the reaction. Now, after this steady state, what happens? You see that the curve curves until that's it. You no longer get more products. What happened here? Why is it curving like that? It doesn't continue steady slope. It curves. Why? Yes. So that's it. You cannot, once you are you lose the substrate, the reaction backwards become more. ES to E plus S becomes driven more. Because now then you are losing substrate, you're not saturating the enzyme anymore. You are driving less production of product. Okay. So whenever you want to measure activity of an enzyme, you really want, or you want to measure a constituent like a product or a substrate, you really want to be in that steady state where you get a linear relationship between the product and the time. So it's very important to know where your steady state is in a chemical reaction. Now, this is the other curve I drew here. Now, how do I get to this other curve? Basically, what I do is I run this multiple times at different concentrations of substrate. So I run the reaction one time at, let's say, concentration of 1 millimole of the substrate. And then I run it again at 5 millimole of the substrate. Every time I get a different slope. And then I plot the slope, which is my initial velocity, at the different concentrations of the substrate. I get now the relationship of velocity to substrate concentration. What do I see on this curve? I see two other things or three other things. I see Km. I see Vmax. I see Vmax over 2. Forget about Vmax over 2 for a second, although it is important to determine Km. But this is going to be the Michaelis-Menten curve that will give me the Michaelis-Menten equation. That in that equation, I will have Vmax, I will have Km, I will have VO, and I'll have substrate concentration. So I want to get an equation that will relate everything together. And when I run my experiment at different substrate concentration, I can calculate Vmax, I can calculate the using the Michaelis-Menten equation. So what I will work with you on right now is deriving that Michaelis-Menten equation, which is basically the relationship of these terms together. Okay. And Michaelis-Menten are the names of the two people that came up. So, yeah, it's always like that, named after the people discoveries. All right, so the initial velocity is obtained at the steady state at different substrate concentration. Vmax is when you reach maximum velocity at when the enzyme is saturated with the substrate. So at a particular substrate concentration, let's say enzyme is saturated. So you are driving the reaction to the maximum rate. And then beyond that saturation, if you keep, if my enzyme is saturated, let's say at 10 millimole per liter of the substrate, if I put 20 millimole, it's not gonna matter. I reach Vmax. So, and now this is Michaelis. I don't know why they call it Michaelis constant. It should be Michaelis Menten. They drop the name of the other person. A Michaelis constant is the substrate concentration. Remember, here's your x-axis is a substrate. So it's substrate concentration at which your velocity equal Vmax over 2. It's a very important constant that we get specific to enzyme and a substrate, a particular enzyme and a particular substrate. And it tells us the affinity of the enzyme to the substrate. Before I go into the next stage, think about it. Don't look ahead, just think about it. If you have lower Km value, do you have higher affinity or lower? Higher. Because now you will have Vmax, half Vmax at much lower concentration. That means the rate of the reaction will proceed faster at lower concentration. That means that's higher affinity. So think of it opposite. Okay. So here's an illustration. So you have substrate 1 and substrate 2. So substrate 1 has a lower Km than substrate 2. At the lower concentration, you get the same velocity, Vmax over 2. So that tells me the first substrate has better affinity to the enzyme than the second substrate. So this is just an illustration of how Km relates to affinity. So Vmax obviously is affected by the nature of the substrate and the enzyme concentration, the parameters of the reaction, whether or not you have inhibitors. And Km also is impacted by not the concentration of the enzyme, but the nature of the enzyme on the substrate, not the concentration. And of course, the conditions where the reaction is happening. Do we have inhibitor or not? Do we have the right pH and right? So Km is not a concentration dependent of the enzyme on the substrate, whereas Vmax is a concentration dependent of substrate and enzyme. Okay. You can stop me if you have questions. Yes, Karen.
Previous slide,
Previous slide.
the x-axis is S0, what is that? S0 divided by K.
The initial concentration. The initial concentration of the substrate. The start. You started, of course, the substrate will be depleted over time, right? So it is what you put in your reaction at first.
So this graph just based on one substrate concentration?
No, this one is based on one substrate concentration. This one is on one substrate concentration. Here, no, you run the reaction at different substrate concentration, and then each substrate concentration, you got a VO, initial velocity. You plot that velocity against the concentration. So when you do enzyme kinetics, and I've done that when I was a postdoc, I have to run the reaction multiple times at different substrate. So it is really annoying to collect data, basically. Which one? The nature, yes. The nature, not the concentration. The nature of the enzyme and the nature of the substrate, because it's basically the affinity of the enzyme to the substrate. Change the enzyme, same substrate, you have different affinity. Change the substrate, same enzyme, you have different affinity. Put an inhibitor, you'll change the affinity.
Why you divide by two?
Oh, not divide, or, because here you also get the KM. Yeah, no, it's not division. Yeah. You got confused by, yeah, sorry, I don't know, this is a very old graph, hint, you want extra points? Okay, so this is slash KM, not divided by KM, and I saw a hand, yeah.
I don't understand why you like lower K1. Is that?
Oh, okay. Let me go to that slide, yes. So what do you see here? So KM1 is lower concentration of substrate than KM2, right? Here is your substrate concentration. There is a red substrate and a blue substrate, two different substrates to the same enzyme. So this is Vmax, this is the midpoint. So this is Vmax over 2. If you project that, and you get 2 kms. Okay. So at the concentration, let's say this is concentration 1, this is concentration 2 millimoles per liter. Just millimoles. Okay. So at 1 millimole, you reach the same velocity as 2 millimole of another substrate. So meaning the enzyme has more affinity to this substrate at lower concentration. So it's more, it has affinity, it binds quickly, the action moves forward. So at lower concentration, you get really high rate for that.
So Vmax cannot change, like,
Vmax,
that's why.
it's the same enzyme, same enzyme.
Yeah.
So, yeah, so two different substrates, same enzyme. At different concentrations, you're gonna reach,
The curve, basically the curve doesn't shift.
doesn't, it might, well, okay, it might shift. I'm not saying it doesn't shift. I'm just rudimentary giving you an example. Assume it does, assume both of them be the same Vmax and the same Vmax over 2. The one that you should be at lower concentration will have better.
So then, if the curve does shift, then.
Think about it, it might shift parallel. It might shift in a parallel manner.
Okay. Because, so like,
You're overthinking it.
okay, yeah. I guess.
You are overthinking. I'll let you overthink alone. But the idea is with higher affinity, meaning at lower concentration, you will have you reach higher velocity. Okay, you can overthink it, and once you overthink it and done, come tell me what you came up with. Okay.
So if you're designing an experiment.
Yeah.
Why do we care about KM? When you want to just be the best, like Vmax, the best concentration? Why do we care about like half?
We care because sometimes having a lot of substrate, it costs money. So you want to reach a perfect reaction rate and time where you use minimal resources. And I'll give you an example about when KM, low KM is beneficial and when low KM is actually bad. It's a good question. That means you're listening and thinking. I didn't include you with all this KM Vmax business. Here's the example. So good consequence of a low KM. So you are trying to produce corn syrup, okay? So of course, you want to have a low KM because you want high binding. So you want good reaction rate at lower substrate concentration, okay? So that you can move forward and quicker in producing corn syrup. So produce more in shorter time. Small Km means a high binding, as it means enzyme is saturated now at lower right? And this is meaning gives you more yield. That's exactly what you want. Now, bad consequence is when you have an enzymatic reaction you don't want, like polyphenol oxidase, brown. You don't want that. So that means at low substrate concentration, you're gonna get really high browning reaction. And this means you don't want that. So now we think about, do we want to do inhibition, heat treatment, putting an inhibitor, and then start thinking that. So sometimes Km, low Km is good, sometimes it's not, depending on the type of the reaction. So when you want to reserve resources, or when you want to inhibit the reaction you don't want. Okay. This is really important, you guys, if you ever work with enzymatic reaction, to either determine a substrate, meaning I want to determine very simple glucose. So glucose oxidase, usually it's the end reaction, either for actual glucose or for starch or for amylose and lactate ratio. So it is really common to measure glucose. So that's why I'll give you an example. So I want to measure glucose. So I want the reaction when I do my enzymatic reaction to be sensitive to the substrate concentration, because my substrate is glucose and I want to determine concentration. So this means I want it to be in the linear place of the curve here. I want my rate of the reaction to be dependent on the concentration of the substrate because I'm measuring substrate. So I want to be here. So I want it to be first order with respect to the substrate. So the substrate concentration has to be much less than Km. So the rate of the reaction should not be dependent on the enzyme concentration. It should be dependent on the substrate. So I want the reaction to be zero order with respect to enzyme and first order with respect to substrate. I don't want the enzyme to be my limiting factor. I want the substrate to be my limiting so I can calculate the substrate concentration. The opposite is true when I want to measure enzyme activity. Like I want to measure alpha amylase activity. I want to measure chymosin activity. I want to measure polyphenol oxidase activity or peroxidase activity, lipoxygenase. I'm giving you all these examples. Alkaline phosphatase. I want to measure enzyme activity. When I want to measure enzyme activity, I need the substrate to saturate the enzyme and not be a limiting factor and not influence the velocity. I want the velocity to be impacted by enzyme concentration because I'm measuring enzyme activity. So now I want my concentration of substrate to be up here, zero order with respect to the substrate. I want the substrate to saturate my enzyme. So if the enzyme activity is different, it would be the top. So first order with respect to enzyme, zero order with respect to substrate concentration much greater. Any question there? Okay.
But when you say it should be zero order for the enzyme action. Right?
Zero order?
Measuring
So-
the takes,
For measuring the substrate.
I know the enzyme concentration.
For measuring enzyme activity? Which one? Are you asking about substrate or enzyme activity? When I'm measuring enzyme activity, I need the substrate not to be limiting.
But we are talking, so how much?
So Km is right here. Huh?
Mhm.
So Km is when you have Vmax over 2. This is the linear component when the velocity is dependent on the concentration. You increase the concentration from here to here, you're increasing
No, isn't it easy to say that Vn,
Vm.
yeah, the maximum velocity is where it is at zero order.
Rate of the reaction. Rate of the reaction. Vm is rate of the reaction. V0 is the rate of the reaction,
VM is the maximum velocity.
maximum velocity.
So it's.
You don't want, when you're measuring enzyme, you don't want to be here. You don't want to be at maximum velocity, otherwise you won't be able to remember the concentration of it. When you're measuring enzyme activity, you don't want to be always at the Vmax. Then you won't differentiate the enzyme. Okay. Where am I using?
I'm trying to think about that.
Yeah, think about it. So when you are measuring an enzyme activity, so you want to put, you dump a lot of substrate in there so that your reaction is not dependent on substrate concentration. That means whatever enzyme you have, amount, it's saturated with, regardless of the amount, because there's a lot of substrate that will saturate 1 millimole, 5 millimole, 10 millimole of the enzyme will be saturated with this stuff. Then you run your, usually when you do lipoxy, you make activity, you understand the player with the activity of the enzyme, not the substrate. Yeah, you want to see on it. Yeah. Okay. All right. Now the fun stuff begins. That was nothing. Good now. Nothing. Okay. So I want to walk you through the Michaelis-Menten equation and how we derive it. So if you remember, what do we want to know? We want to know Km and Vmax. So I want to use this curve here, this relationship that we're seeing, to come to an equation that I can actually calculate Vmax and Km. Okay, because these are important parameters for setting up my enzymatic reaction. Okay, so now I want to start with some given, so I can get to the Michaelis-Menten equation. All right, what is this? Initial velocity. Initial velocity, remember, is the slope at the steady state. So the initial velocity equal this K2, very important, multiplied by the concentration of the complex, ES. So you have the rate constant multiplied by the concentration of the ES complex. So that is your initial velocity. So at the steady state, we are at the steady state. At the steady state, you have something we call rate of disappearance, and then we have rate of appearance. Okay. So at the steady state, rate of disappearance equal rate of appearance. Let's look at rate of disappearance. That means the ES is going back to E plus S, and it's going forward to E plus P. So the rate constant of the backward reaction and the rate constant of the forward reaction. So these two, okay? The rate of appearance is only the first one, E plus S. So concentration of enzyme, concentration of the substrate, by the rate constant that goes the first appearance of the ES. So, okay, right, are we following so far? Okay, very good, very good. Now, at that steady state, these two are equal. Okay, this is equal to this. All right, so now in this reaction, I have the free enzyme and I have the enzyme complex. All right, so I don't know how to get the enzyme because it's hard to get, but I know the total enzyme. I know the total enzyme because I know how much enzyme I put in the reaction. So if I substitute with the total enzyme, then I get the E0 here, the total enzyme, the initial enzyme, whatever you want to call it, and the complex. So I only removed that 3 enzyme. Now I want to start gathering all the constants into one constant, the K1, K minus 1, K2. So this is it. The common factor here is ES. I take it out. And then I have the K1 here. So I move things around. So I get all the K's together. This is K. K minus 1 plus K2 over K1 is Km. So it's just a matter of resubstituting, rearranging to get to the enzyme substrate complex here. Everything in here should be able to calculate or determine. Okay, so now I'm going to bring this over the same equation right there. And I'm replacing all the K's with Km. And then I'm bringing the first equation that I showed you, which is the initial velocity. So now I want to find an equation that has initial velocity, it has the substrate, and it has the Km in it. So I take the ES out, and I have the total enzyme, the substrate concentration, the Km. So all of these now are starting, is bringing me to that equation that I'll be able to calculate Vmax and Km. So I'm just bringing those over. So these two are here. Over. Okay. So when all of the enzyme is saturated with the substrate, we have Vmax. And this happens when you have the concentration of the substrate much greater than the Km. So now the initial velocity becomes Vmax, okay? So this K2 into E0 is now K2 into ES. So that's Vmax. So now Vmax is equal K2 into E0. So here's that. K2 into E0 is Vmax. This happens when the enzyme is saturated. So instead of ES, now all of the enzyme is saturated, so I can replace ES with E0. I can interchange these two. That's why I can replace here with Vmax. So now I have initial velocity, Vmax, substrate, Km. So these are the values that I wanted to find a relationship, an equation that has all of them. So there's your initial velocity, there's your Km, there's the substrate concentration, and that's your Vmax. So they're all in one equation. Now you will have to spend a hot minute, right? Gen Z says a hot minute. You'll have to spend a hot minute thinking about that derivation, okay? It will all make sense when you just slowly look at it and just say, okay, I need to reach an equation where I have all of these related to each other so that I can run a reaction and get Vmax and Km, okay, from this curve. And that is the famous equation. But you know, we like simplicity. And linear relationship is always our favorite. So another pair of smart people came along. You know who these guys, you've heard of this term, right? Lineweaver-Burke, another two smart people, said, you know, linear relationship is always good. Let's invert the Michaelis-Menten equation down here, get the inverse, and they smartly got a linear line equation. So 1 over V initial velocity is your y, okay? Km over v max is your slope, y equal ax plus b. That's a linear line. So this is your slope. 1 over substrate concentration is your x. That's your variable. That's your dependent variable. And then 1 over v max is your intercept. So y equal ax plus b. Simple. Now, it's really easy. You have your b value, intercept. You can calculate Vm very easily from the equation of the line. You have the b, the intercept. You get V max. And then if you get V max and you have the slope, which is A, and the slope equal Km over V, you can calculate Km. And Y and X are your independent and dependent variables. So there you have it. You got Km and you got V max in one equation. Easy peasy. Nice and cheesy. Who says that? Which person? Right. In the cartoon, he says, easy peasy, nice and cheesy. You have no idea. Oh, Mr. Robinson, the bowler head guy. Easy peasy, nice and cheesy. You know,
This only true when the substrate concentration is like saturated.
yes. So the method, when you want to determine Km over V max, you want to saturate the enzyme with the substrate. Otherwise, all your calculation will be wrong. I did that.
But then, like, piggyback off that, then it has to be to figure out like what concentration, like minimum concentration.
Yeah, you have to experiment. Make sure that you reach, you put the concentration on the enzyme and calculate V0. And then if you add the concentration and V0 doesn't change, you say, you always have to do that preliminary regular. Start with so that you can characterize the enzyme. All right. So what you would do in this case is you run the experiment at multiple substrate concentrations and get your V0 and plot your Lineweaver-Burke plot. Okay. So I'll give you an example that I've done also as part of my postdoc research. So here I looked at isoflavones. So 3 types of isoflavones common in soy. And these 3 forms have a glucose moiety attached to it. So that you have the phenolic compound with a glucose. Each one of them has a phenolic part and then a glucose. In order for us to physiologically benefit from them, the glucose should be broken up. So it should be broken up by glucosidase enzyme, and we have glucosidase in the gut. So the purpose of the experiment is to determine which of these are more bioavailable. So which of these will be hydrolyzed best, more efficiently with beta glucosidase, so that we determine which one is more potent. So I did kinetics with the same enzyme and 3 different substrates and determined the Km and V max of each of them. Looking at this and looking at the slope, Km over V max, which one of the 3 or 2 of the 3 or 1 of the 3, I'm not going to give it away, either 1 of the 3 or 2 of the 3 is our least bioavailable. Hydrolyzed the least bioavailable. Huh? Lecithin, yes. It has the highest slope. So Km is high compared to Vm. So the Km is way over there. And then the inverse of that means is the velocity is lower. That means the enzyme had more affinity to diazine and genistein. So these two are much more bioavailable because the enzyme in our gut will have more affinity to them than the other one. Yeah. So low Vm and low Kcat over Km, this is catalytic efficiency. Kcat is Vmax over total enzyme. That's another term we calculate when we do kinetics of an enzyme. And so as the Km is higher, the catalytic efficiency will be lower. So basically, glycine has the lowest catalytic efficiency. What? No, I have more time. I'll leave it till later. Okay, we have more time. I'm sure you're enjoying this. I can see the joy in your eyes. Well, at least I'm enjoying it. I like enzymes. So factors that affect the enzyme reaction rate, we're gonna look at enzyme concentration now. We talked about substrate concentration. Now let's talk about enzyme concentration. Everything we have talked about initially was just varying the enzyme, the substrate concentration. Now, if I vary the enzyme concentration, obviously I'm going to enhance, assuming that I have enough substrate. So that means the enzyme is saturated with the substrate. Substrate is not a limiting factor. I would see a linear relationship if the substrate is present in sufficient amount. As the enzyme concentration increases, the observed velocity increases. And that's how we can measure enzyme activity, because we know that the velocity will increase when the enzyme concentration will increase if I have enough substrate in my reaction. Okay. But here is a very important caveat. At some point, I need to select an enzyme concentration. If I'm monitoring a reaction and I want to determine the product or the substrate concentration, I want to select an enzyme concentration that is most efficient, but most accurate predictor. And I want to select the time of the reaction that I can control and I can measure. It's enough for me for the reaction to go and measure. I don't want to have a reaction time of 1 minute, for example. If I'm running an experiment and I'm pipetting and I want to put it in the spectrophotometer, I need a little bit of time so that it's not a very quick reaction. So the time component, I don't know what I did. The time component is very important, and the enzyme concentration is very important. Because look what happens if I use the highest concentration number 4. I only have a very short period of time where I have linearity. Otherwise, I'm going to get this curve. Why? Why am I going to get this curve? Substrate depletion. So substrate depletion is really high and very quick. I can't control the reaction. It's very quick. It's like a 30 seconds. Then I go, okay, let's look at the lower concentration. At this time that I'm comfortable with, 30 minutes, I'm also not at the exact prediction of linearity. I'm also getting this depletion. So with enzyme concentration number 2 here, I'm able to get good reading in my target time, and the reaction is still linear. So I'm not depleting the substrate very quickly. So, and this might, the last one, I might not have sensitivity. So it might be below my absorbance range, close to noise. So I don't want that. Otherwise, I need 3 hours of a reaction. So in designing those enzymatic reactions, see with me that you really need to consider many factors: the time, the linearity of your curve, the substrate concentration, the enzyme concentration. So what you do in the lab, you follow an SOP or you follow a tip. You don't think about it. You just do the steps. But a lot goes into designing those. So appreciation time. Yeah, so this is just showing you that dotted line is basically the depletion, the same figure. Okay, so now substrate concentration, we talked about it a lot. And we have the saturation effect. We have the linear here if you want to measure substrate. So first order here in this area, 0 order up here. But if you have really high concentration, sometimes the substrate binds at multiple locations on the enzyme, stereochemically and not, in the binding in the active site and another site, and actually inhibits the enzyme. So sometimes we get this substrate inhibition, so we have to be careful. And sometimes we need a minimum concentration to actually activate the enzyme and initiate the reaction. So a very complex kind of relationship between this enzyme and substrate. This is easy. You all know this. You increase the temperature, you have more thermodynamic, you enhance the reaction. But because enzymes that we work with are proteins, you reach a denaturation temperature. And this is different. That's why I don't put temperature here, or this old curve doesn't have temperature here, because every enzyme denatures at different temperatures. Once denaturation is reached, we see a very steep decrease in the reaction. So theoretically, you would say with increasing temperature, you really get enhanced activity. But no, you reach a point of denaturation and it drops. And every enzyme is different. So that temperature will be different. In terms of pH, also you have an optimum pH. It's not always pH 6, by the way. It can be some enzymes like pepsin, pH 2, some enzymes like trypsin, 7.5 to 8. So it really varies, that optimum pH. And as you go away from the optimum pH, the activity drops because it's a protein. Remember the ionization differ. And when the ionization differ changes, the charges are different, the active site changes, no longer perceptive to the binding site on the substrate. So that's why we lose activity, because now the ionization state is not the perfect one that gives you the maximum binding. Okay, now there is pH stability though. Stability is different. It has to do with the denaturation of the enzyme. For example, trypsin is stable at pH 3, meaning it's still not denatured. If the pH is 3 at room temperature, it's not denatured. If you bring it back to pH 7.5 and 8, it will work. But some enzymes are more sensitive to pH. They might denature at low pH, especially if you increase the temperature. If you heat, they will denature. So there is a difference between stability versus optimum. So it doesn't mean that if the pH is not optimum, you denature the protein or the enzyme. Every enzyme is different. Okay.
When you mentioned before the temperature,
Mhm.
I thought about the thermostable enzymes.
Yes.
Also have a temperature where they will denature, but that is much higher than others.
Yes. So the activity will, so of course, initiation is a cumulative reaction. So you will have partial and the activity will reduce until you get complete initiation. So let's say thermostable enzymes, especially microbial enzymes, very stable. So then you might not denature them completely, but you will lose activity because you're partially changing them. Denaturation can start at as low as 40. It's time. Okay. So environmental factors. So that's what we call it usually. The common name is cofactors, but if you want to think about them differently, you have the prosthetic groups that bind irreversibly. So, for example, aminotransferase enzyme, the cofactor for it is vitamin or the active form of vitamin B6, pyridoxal phosphate. So that once it binds, it's irreversible and it just maintains the activity of the enzyme. But then we have organic ions that dissociate. And these organic ions, like I said, that it can be an enzyme requires a chloride, a Cr minus, an enzyme requires a calcium to work. So these would be the inorganic ions. And then you have the coenzymes like NAD or NADP. So here you have this alcohol dehydrogenase. You really need that cofactor or coenzyme here for it to work. Because of it is related to the proton acceptance enzyme. Okay. Now inhibitor. So going back to what is uncompetitive inhibitor and competitive inhibitor. Okay, so we have two types of inhibitors. You have the irreversible inhibitors. That means once they are there and they bind to the enzyme, that's it. Bye-bye enzyme. They are inhibiting the enzyme. Dissociation constant is very small. That means once they're associated, that's it. The decrease in enzyme activity is related to the amount of inhibitor added, but sometimes it takes a little bit of time for the reaction between the inhibitor and the enzyme to occur. So amylase inhibitor is irreversible inhibitor. So it is found in legume, and if you want to measure its inhibition, you really need to incubate it for a little bit with amylase before you start measuring the reaction, the enzymatic reaction. All right, so here's the illustration of the irreversible inhibition and the three types of irreversible inhibition. So you have comparative inhibition, which is the most common most common reversible inhibitor. So look at this illustration. So you have succinate and malonate. So look at them. They are structurally very similar. The only difference is a methyl group. So succinate has a methyl group additional to the one methyl group in malonate. Okay. So that's the only difference. So they both compete for the binding site of the enzyme. However, succinate, when it binds to the enzyme, it gives the product and the enzyme, whereas the malonate, competitive inhibition, when it binds, nothing happens, no product. So these two have similar structures, so they compete for the active site of the enzyme. And when you do kinetics to understand the type of inhibition, The competitive inhibitor gives you this kind of Lineweaver-Burke plot. So you have one with the inhibitor, one without the inhibitor. You notice that the slope is steeper when you have the inhibitor, but then you have the intercept is the same. So basically, the competitive inhibition does not affect the rate of the reaction when you already have the enzyme and substrate complex form. When the enzyme and substrate complex forms, the rate of the reaction is the same. But what it does, it actually changes Km. The Km is different. The Km goes up. But the Km goes up, meaning because you have competition, now we're losing affinity to our substrate. So the Km goes. So when you're running kinetics and we see the same Vmax, but a larger Km, that is competitive inhibition. So in cases you want to have a competition, a good competitor, so when you want more substrate, you want to slow down an undesirable reaction. So when you want to slow down an undesirable reaction at polyphenol oxidase, you want a competitive inhibitor that reduces Km. That increases Km. So an undesirable competitor, so when we have Km being, when the Km increases, that means, oh, just not to confuse you about labeling, Kmi is the affinity to the inhibitor is lower than Km of inhibitor. Okay, Km of inhibitor is lower than the Km of the substrate. That means the enzyme has more affinity to the inhibitor. Okay. And then here, so when you have more affinity to the inhibitor, it would be a good competitor if you want to stop a reaction. But it would be really bad if you want the reaction to proceed, which will impact the rate. So these are just two examples of a good and a bad, depending on, do you want the reaction to proceed or you don't want the reaction to proceed? And now you know Kmi for the inhibitor is lower than Km without an inhibitor. Okay, so non-competitive inhibition. So the non-competitive inhibition, meaning your enzyme is not competing, well, sorry, your competitor, your inhibitor, sorry. Your inhibitor is not competing with the substrate. It's binding at a different location of the enzyme. So it binds at a different place. So it changes the conformation of the enzyme, and now the substrate won't bind to it. So that means when the inhibitor is there, that non-competitive inhibitor, depending on the concentration of that inhibitor, most of your enzymes are now not able to bind to the substrate. But some enzymes still bind to the substrate if they don't have that inhibitor. Because some of the enzymes bind and some don't bind, the rate of the reaction will be impacted, not the affinity. If you don't have an inhibitor bound, the affinity does not change. But because some of your enzymes in your mixture are bound to the inhibitor and some are not, the total available enzymes for the reaction is lower than the velocity difference. So in this example, your velocity is impacted, not the Km. Good? Yeah. Reversible. Because that's why in a solution, you have the inhibitor, the enzyme, the substrate. So when the enzyme is bound to the inhibitor, it doesn't bind to the substrate. But then the inhibitor might dissociate and then the substrate will bind. This would delay the reaction. Inhibitor is binding, not binding, substrate is. So less enzyme is bound to the substrate. So it's not the affinity that's impacted, it's how much reaction is happening. So the velocity is impacted. It's like decreasing the concentration of the enzyme. Okay. And then the uncompetitive, I don't know why they called it that. They could have come up with another creative name. It's confusing. This one binds to the complex. It binds to ES. So the enzyme and substrate bind, and then the inhibitor binds to that complex, prevent the reaction from going forward. So here, really, you get a parallel. You are impacting the whole reaction. So you're reducing the velocity and you're impacting things. So you see a parallel shift. It's not very common inhibitor, so don't worry much about it, other than it means that the inhibitor binds to the complex. And now is a good stop. All right. Saturated, like the enzyme with the substrate. Okay, well, I'll see you next week. Hopefully I will finish enzymes and start protein, dairy, I think. Okay. All right, and I will probably bring your exams.
All the presentations on the April 30th, that will.
Oh,
Yes.
yeah, we will all be at AOCS. Wait, don't go. Yeah, now you can go.
Yeah, I think it's close to my house.
Yeah, I think it's me and you on April 30th. That we won't go, so I was wondering if we were earlier.
Oh, I really don't. I'll be doing it. In my presentations on Monday and Tuesday. I thought I won't be here. What do you think? Before you go, what about Tuesday, the 31st, right? Do you have classes between 3 and 5 on Thursday? So for that week, which is the last week of classes, can we have a class on Thursday instead of Wednesday? Okay. What are we, April 30, yeah, May 1st. Yeah. Thursday, you're all good? Good, you have classes or no? All right, very good. So I will send an email to confirm that the last week of classes will happen April, May. Yeah, okay. Sounds good. You are presenting on Wednesday. That's bad. The last day, you did it with the lead. Yeah, that's people. Okay, doke. I will see you next week. Thank you. Yes. Let me stop sharing. Exit. Wait, I need to stop recording. Okay. This card. And then where's it?